Hey, thank you so much. I think I should say good morning there in Hawaii, and basically greeting from cold and windy South Dakota. I wish I was there too. Uh, Today I want to talk about a recent research project that we completed and that was part of Tri-Leader Center on repairable precast bridge columns. I hope you can also see my pointer. I'll go ahead if not, but it's not neither really. But I would like to thank my graduate students, Ted and Cal. They worked very, very hard on this project, and I really appreciate their patience and hard work. I also would like to thank our sponsors, PCI, Charter Lee for sure, USDOT, and one of the 4 columns that I'm going to present here on repairable columns, 2 of those were basically sponsored by MPC, another UTC center, but the 2 good ones that will be focused of today was sponsored by PCI and Charter Lee. So I really appreciate everyone's feedback and input and support of the project. I will do a quick background, really motivation of why we did what we did, and give you some feasible detailing on repairable columns and the experimental work that we did, and kind of conclude the work with some highlights of our study and the key findings. Okay, you may like this slide, but that was really the motivation of this study. I have Chevy Sparks on the screen, less than $14,000. And I also have Rolls-Royce boat tail, and you may not guess the price, $28 million. Okay, the cheapest car in the world, or in the US, and the most expensive car in the world. If these 2 guys collide, we can repair them because both have been designed with the prefabrication modular idea behind. While for us as a structural engineer, as a bridge engineer, we do not think that way. If a column of a building, multi-million-dollar asset is damaged, or a beam of that damage is beyond the repair point, you have to demo your multi-million-dollar asset, spend another few $1,000,000 to rebuild it. And we want to see if there is any opportunity or possibility that we can bring this modular construction with the idea of repair them wherever you need them into bridge engineering. So that was really the motivation of our work. And I'll dive into the detailing that we develop. I want to give you an overall perspective what a repairable detailing will look like for a bridge column from our side. For conventional construction, you have your footing, you cast on side, then you assemble the cage. Part of that was built with the footing, and then you pour the column, and that's your conventional cast in place construction. For repairable detailing, we propose your footing can be cast in place or precast. I show one picture of one of the specimens that we tested here. Your column has to be fully precast. Here is another picture for it. And because these 2 guys will be connected through a dry joint, you probably need a shear key to make sure that it does not fail at large displacement and large, basically, forces. So that's the detailing of the shear key. In one option, you can have a steel pipe or shaft embedded into column or in the footing, and you can have a matching socket on the other side to take care of the shear. Here is one example for it. And at this time, your column is pin-pinned, doesn't have any moment into it. To be able to develop moment, we are proposing 2 types of external fuses. That's where we started with a miniature BRB. We call it BRR, What it is a dog bone bar. It can be straight bar too, and you can encase it in steel tube and fill it with grout. So it's kind of miniature BRB that is used in steel structures, but at the bar size for bridge application. But then we came up with the idea, why not using just a steel tendon as your exposed fuse and try to see how the behavior of that one works. So the combination of fuse and the shear pin will generate moment and shear, and that would be a moment resisting joint. I think I'm hearing myself back. Probably audience need to mute themselves. Okay, so that one was the one kind of let's say repairable detailing that you might have. We did not develop just one detailing, we developed 20 detailings, feasible ones with the current material or state-of-the-art materials. Okay, number one, I talked about it. That was my previous slide. Number two, you might use UHPC or ECC to improve the performance of the column and basically reduce the damage. You might completely replace your shaft, your small neck region with a steel pipe and go with that option. You might also have part of the column precast, and then the steel pipe can be cast in place through a socket. And the list goes on. You can have a full column precast as well with both end bars embedded into column, and then you post tension it, you ship it on site, and then there is a socket in the footing, can assemble that. So multiple different detailing. We wanted to know which one is really the best. So there is quantitative evaluation technique developed in the NCHRP 864 project. It will uses 13 parameters like displacement capacity, plastic hinge damage, and residual damage, and what tools you have at the time of design, and we will tell you if this new concept is a good concept to be adopted for field or testing, whatever aim you have. So we used that and we evaluated all 20 options we had, and we came up with 4 columns ranking 1, 2, 3. Last one will be shared between 2 detailing with exactly same number. So column number 1 out of these 20, the best one is the one that column is precast. You have ECC or UHPC, you have your piping, and you can use any kind of exposed fuse there. Number 2 has the similar ideology, but you use conventional concrete or a CC, and you might have your pipe inside the footing, but not inside your pipe will be inside the column, not in the footing. And you can also post tension your column. To be able to allow that detailing, you have to have your column fully precast and have kind of ABC connection to connect it. That one became our number 3, shared with this option as well, which you have basically a dry joint and you will do post tensioning on site. So number 1, 2, 3 were the best for us in this project to test, because we understand that this detailing might be a bit difficult on site. If we can do everything in a factory and just ship it on site and then take it from there, that would be the best option. So we started testing these options one at a time. We started really with this option, and then we tested the next 2. I'll quickly go over the experimental program that we had. Or base column, conventional cast in place, we call it CIP no one, was an octagonal column with 24 inches in side to side or dimension, and 8 feet tall in terms of the length of the column. We had actuator, we had load cells, we had hydraulic jacks to apply axial and lateral loads. We pushed the columns back and forth, and that's how we tested basically all of these columns. For the first precast column with the repairable detailing, we asked a precast plant to build it for us. We wanted to keep them involved in the project. Gage Brothers in Sioux Falls, one of the leading precast industry in Midwest, and they built the first specimen with SCC, shipped it to us. We had the footing here in our lab. You can see there is a matching socket in the footing. And then we also use a stainless steel everywhere, and our fuses were duck bone stainless steel cast into a steel pipe. Then we filled the pipe with basically grout and made a miniature BRB. We lowered the column into place. We use a steel plate to minimize damage at the time of rocking, and is kind of the finished test setup of the first column with conventional, or let's say SCC, and you have your BRRs attached to it. Here's kind of a more close look at the BRR, and there are mechanical bar splices at the end of the bar to attach and detach these yellow guys at any time that you want. And we also use some split nuts at the end. At that time, I thought maybe this exposed bar will buckle here, so we kind of confine them here as well. And it's kind of a closer look of the split nuts there. That was our first specimen. In the second specimen, we have the same ideology, but we use UHPC on the entire length of the column. Footing we built here at our lab. The UHPC column was built by Gage Brothers in Sioux Falls. This time we had our steel pipe inside the footing, and then there was a matching socket at the base of the column. In collaboration with HRC, we invented the first of its kind coupler that can connect the steel bars to steel tendon. And that was very cool. And you will see a video of that later in my presentation, how nice these guys will react. And it's better than steel bar confined with tube, because let tendon to buckle, nothing will happen to it, and you can use it in tension only. And here is kind of a close-up of the shear mechanism that we had inside the column. They're over-designed because we didn't want to test them at this stage. The actual design can be smaller as well. And the assembly was very easy. Lowered the column, then attach these tendons. We also placed some lateral bolts to minimize the gap between or basically kill the gap between the pipe inside the footing and socket inside the column, so the column does not have any slag at the small forces. The third column that we tested has the same, again, technique, but the column was completely built with UHPC with the bottom portion. And then there was a matching socket in the footing. This would allow us to post tension the column right at the factory. And you see the tendons and how the post tensioning was done at the precast plant. They shipped the entire column post tension version to us. We lowered the column down the footing. We filled it with grout, as easy as that. We just made sure that it's plumb. Column is ready to go. Attach your exposed tendons. And then the overall next section, we call it, was 24 inches in all of our projects. That both would give us about 15 inches of clear tendon between the two couplers. So here you are seeing the damage of the 4 specimens at 1% drift ratio. This is where usually CIPs will yield. You can see some shear cracking and some basically flexural cracks at CIP. In the SCC column or first specimen with BRR, some minor damages down there at the rocking face. On the 2 UHPC columns, we had 1 cracking or 2 here and 1 or 2 cracking here at 1% drift. Then we pushed it to 2, 3, 4, 5 to 10%. I'm showing the result at 3%, basically drift ratio, spalling of conventional column. The repairable column with SCC and BRR had some more cracking and some spalling at the base. The two column with UHPC, again, almost no cracking, no damage, and some cracking here and there, very, very minimal at basically 3% drift. At 5, what we did, we stopped all of our repairable column. We took out all of these exposed fuses, put new ones, and retested all of the repairable columns from start to failure. So conventional one, we started from 0 to 10% wherever it failed. The repairable columns, we paused at 4 or 5% drift ratio, repaired it just by replacing these exposed components, and then retested them. Just to give you a number, these two columns, it took us less than 2 hours to take the tendons out, put new strain gauges, prepare the test setup, and start testing. So only 2 hours you can repair your column at 4 or 5% drift ratio. Very, very fast repair strategy. What we noticed that the one with conventional concrete or with SCC and BRR starts to push concrete in compression, because these guys are designed to take compressive forces beside the tensile. However, the specimens with tendons won't generate any compression. Your columns are good, healthy, no issue with those columns. You're seeing damage at 8% drift. You can see a Z-shaped buckling of these miniature BRRs. Your CIP is at bad shape, it's close to failure point. Still, you can take these guys out and repair them. Hard for this one, but for these two, very, very easy, because still we're seeing no damage. I'll talk about residual displacement, very, very small for the last two columns. And here is the damage at the failure of all of these columns. CIP, bars, basically buckled and fractured. These guys didn't fail. We stopped test at 10%. We had tendon rupture in the third basically specimen with UHPC, and the last column we had some internal bars running at the footing level, and those guys ruptured, so we stopped test. The fuses did not really rupture. So here is kind of video. I hope there you can see the video. I won't talk about the compressive behavior of these couplers. The video is annotated, so I hope that you can see. So the column is being pushed toward us. Look at the tendons, how they behave. So what happens is, when you put tension in these cables, they stretch, they go beyond the yield point. Then when you compress them, they just slide back into their wedges. They are tight now, and in the retesting in tension, you don't have any slack. So they start from this slipped version, and that was very, very interesting to see. And the next video will show you the failure of these tendons. Hopefully you can see also the sparks, that when they failed, you will see the sparks. Okay, just for the safety purpose, I wanted these tendons be basically covered, so we use a transparent hose around them. That's what popped out. So it was not tendon, it was just the hose that we had as a cover for them. So let's see how the force deformation behavior of these four test specimens will look like. The black is conventional CIP, very stable, and showed very high drift ratio, about 9%. Drift ratio is lateral displacement normalized to length of the column. The column with the BRR, the yellow one, showed about 10% drift ratio. They did not fail, but the repair of this column at 5% was really tough, because you could see the Z-shaped buckling of the bars. So overall good. The one blue colored here is the one that has tendon basically exposed. The behavior is softer or much softer than CIP. Most likely we need to investigate how much the effect of the softer behavior will be on the system. Like will be there will be definitely more displacement demands on the bridge. Yes.
We are running out of time.
Yes, I have 2-3 more slides to go. We're good.
If you could wrap up in 1 minute, that would be great.
Yes, absolutely. And we need to investigate how much the effect of the softer behavior will look like, but it was super easy to repair this column at 4 or 5% drift ratio. And the last one, which had internal tendons and external tendons, much stiffer behavior closer to CIP, and it was very easy to repair it at 4% drift ratio and retest it. Here's kind of cyclic behavior of those columns. The one that I want to highlight here is the one with external tendons. You see a nice flag-shaped behavior. It means that you will end up with very small residual displacement, even at 8% drift ratio. That would allow you to replace this exposed tendons easy. And with that, I will just talk about in a second about this residual displacement graph. This is how much bridge we'll see after the load. We'll come back to zero displacement, or we'll show some residual ones. The one that with exposed tendon and UHPC shows less than 1% residual drift at 9% drift. So very small, you should be able to repair that. So with that, I'll stop here. And if you have any questions, I'll be happy to answer those.
Thank you, Dr. Tazarv. We have time for like quick one question if you have. Okay. If you do have questions, please contact Dr. Tazarv. Yes, please contact Dr. Tazarv. Okay, so we'll move on to the next presenter. So thank you so much, Dr. Tazarv. So I'm moving on to